So, seeing about Diffie Hellman algorithm, uh, it is used for exchanging keys which are secret and only to be known by the ones sending and receiving. Generally, the keys can be hacked by the third person, or if shared through an insecure channel, they can be seen by others. To avoid this, we'll be using Diffie-Hellman algorithm. It's not used for encryption nor it provides digital signatures, but it can be used to generate secret keys which can be used by sender and receiver, and these keys can further be used for other encryptions. So we'll be seeing how the algorithm works. Generally, there are five parts in this algorithm. The public elements, like the as it is it is also asymmetric. That means we'll be using the public keys and the private keys, as we have seen in the AES and RSA. We'll be using public and private keys. Public keys will be known to every person, like it is public. And there are also two other parameters like alpha and q. We'll be seeing what is alpha and q now. So q is any prime number which is taken randomly by the sender, and in general it must be a large prime number. And alpha is another prime parameter which is primitive root of q, and it should be less than q. The value of q, alpha should be less than q, and q is a prime number. So we'll be seeing what is primitive root. As a marked in red color, you can see that alpha mod q, alpha square mod q. So we'll be finding all the values of alpha mod q, alpha square mod q, likewise, like alpha power q minus 1 mod q. And these values must lie in the range of 1 to q minus 1. Where if we select q as 7 and alpha we have selected 3, and 3 is less than 7, and we'll be finding all the values like 3 mod 7, 3 square mod 7, 3 cube mod 7 until 3 power 6 mod 7. And this values must be lie between 1 to 6, where 6 is q minus 1, that is 7 minus 1. So if these values lie between 1 to q minus 1 and are not repeating, then we can say that alpha is a primitive root of q. So we'll be selecting these two values which are public, which are also public elements, and then we'll be selecting private keys. So these private keys are selected in random by the sender and also the receiver. For instance, let us assume that XA is the private key of the sender, and its value should also be less than Q, where Q is a prime number, as I have already said. Let us assume Q is 7. So the private key we have to select must be less than 7. And after selecting the private keys, that is XA and XB for the receiver, we'll be calculating these public key values. And for calculation, we'll be using this formula: alpha power XA mod Q, where alpha is the primitive root, as I have already said, and XA is the private key of this sender. As private key is already known by the sender, we can use it to calculate. So YA, which is the public key of the sender, it's calculated as alpha power XA. XA, where is it, is private key mod Q, where Q is a prime number we have selected in the beginning. Likewise, we'll be also calculating the public key of the receiver, YB, which is alpha power XB mod Q. After calculating the public keys, it will be visible to the sender and receiver. It will be shared to both of them. Next, we'll be calculating the secret key. The whole Diffie algorithm lies in calculating the secret key. We'll be seeing why calculation of secret key is important. Now, first we'll be calculating the secret key at the sender side. So for that, we'll be using the public key of the receiver, which is YB, as I have written in the heading, public key of the receiver. Power, private key of the sender, as private key of the sender is only known to the sender and none of the other users in the network will be knowing it. It can be used for safety purpose. So we'll be using public key of the receiver, power, private key of the sender, mod Q. We'll be storing it. It will not be shared to in the network. It will be kept aside. That private key, sorry, secret key. Next, we'll be calculating the secret key for the receiver also. How see, it is quite opposite to it. So we'll be using the public key of the sender, power, secret key of the receiver, mod Q. So these two values k and k should be equal. Only then we can say that the Diffie algorithm, Hellman algorithm works. We'll be seeing an example to understand it more properly. So, okay. Now consider Alice and Bob as Alice is the sender and Bob is the receiver. And consider that they are using an insecure channel which is being monitored by some third person, call it Eve. So to provide security and to not to like the key we are using should not be known to the third person. So we will be using Diffie-Hellman algorithm. So as I said in the beginning, we'll be using an alpha value and a q value, where q is a prime number and alpha is a primitive root of that prime number. So we'll be seeing in this example, we are considering the prime number as 17 and the alpha value as 3. It will be shared publicly as a public component. So that 3 and 17 will be visible to the Bob and as well as the third person Eve. Next, we'll be calculating the public key values of the sender and receiver by using the private keys. So let us assume 15, which is less than 17. As I have said, that private keys should also be less than the prime number we have selected in the beginning. So we have Alice has selected 15 as its private key. So now after selecting the private key, we'll be calculating the public key. The calculation, as I've said, will be as alpha power private key mod q, where alpha is 3 and private key is 15 and mod q value is 17. And the resulting value will be 6, which will also be shared across the network. So the 6 value will be visible to Bob as well as Eve. Next, the Bob now will be selecting randomly a private key, which is 13, which is also less than 17, and then we'll be calculating its public key, which is 3 power 13 mod 17, and its value is 12. Now this 12 value will be shared in the network, that is to Alice and as well as Eve. Now this 12 and 6, which are the public keys of Alice and Bob, will be used to calculate the secret key, which might be used for further encryption process. So now 12, 12, which is a public key of Bob, is used by Alice in with help of the private key of Alice to calculate the secret key. That is 12, which is the public key of Bob, power private key of Alice, which is 15, mod 17 is the key value, and its value is 10. Now we'll be using 6, which is the public key of the Alice, power 13, which is the private key of the Bob, mod 17. And its value also must be same, that is 10. It is the key. No, this forms the major part of this Diffie-Hellman algorithm. This algorithm is correct, and the procedure we have followed until the values we have selected and the procedure followed is only correct if we get the same values, that is 10 and 10, the secret key with same. Now you might be thinking that how these values 10 and 10 are same. We'll be seeing behind the scenes like how these values are same.
Came from Bob was calculated as 3 to the power 13 mod 17. So her calculation was the same as 3 to the power 13 to the power 15.
So the 3 power 13 mod 17 is 12 as we have seen. That is the public key of the Bob. We have calculated in the beginning. So how is it calculated? We are calculating by alpha power the private key of Bob mod 17, which is 3 power 13 mod 17. And this the value public key value is sent to Alice. Now Alice is calculating the secret key by using the public key of Bob like 12 power 15 mod 17, which can be written as 3 power 13 power 15 mod 17.
Now consider Bob. The 6 he received from Alice was calculated as 3 to the power 15 mod 17. So his calculation was the same as 3 to the power 15 to the power 13. Notice they did the same calculation with the exponents in a different the exponent, the result doesn't change. But they both calculated 3 raised to the power of their private numbers. Without one of these private numbers, 15 or 13, Eve won't be able to find the solution.
So now Eve doesn't know the private keys of Alice and Bob. Even if the third person tries to crack it by using some algorithm, generally it will take a lot amount of time. In this case, we have taken the prime numbers and all these values as a small value. But in reality, they will be using a larger prime number. So for cracking that larger prime number and calculating all these combinations will be difficult.
Now let's start.
So if this is the Diffie-Hellman algorithm, if you want, I'll also be sharing another example. And if you have any doubts, you can ask me.
Yes, ma, go for another example. Any doubts?
So we'll be seeing another example. Let us assume the prime number as 13 and the alpha value, which can also be called as generator, as 6. As we can see that 6 must be less than the prime number, the selected Q value. So 6, it is 6, less than 13. Next, we'll be selecting private keys of the sender and receiver. And those values should also be less than 13, and which are as 5 and 6. Let me point out. So 5 and 4 are selected in random such that they are less than 13. Where 13 is also selected in random, and in general it should be a large prime number. For our convenience, we are using 13. And P should, which is primitive root, should be a primitive root of 13, also must be less than 13. So the first step is over. Randomly generating a private key and using the agreed upon numbers. Like it will be, these numbers will be known to both Bob and, like for instance, Alice and Bob. Now we'll be calculating the public key. The public key is calculated as alpha. So G is here alpha. Alpha power private key. private key of the sender as well as the receiver. Mod P. We can say, as I've said, Q. Okay, it is Q. So Q value is 13 and alpha value is 6. So 6 power private key. Private key is 5 of the Alice. Mod 13, where 13 is the prime number we have selected. So its value is 2. So now public key of Alice will be 2. Now we'll be calculating in a similar instance the public key value of Bob. So 6 power 4, where 4 is the private key of Bob and 6 is the selected alpha value and 13 is the selected prime number. So after performing this operation, we'll be getting public key as 9. Now this public key is open for all. That is, it will be known for Alice and Bob. Now this public keys will be used by Alice and Bob for calculating the shared secret key, which will not be on the network. No, it will not be shared over the network, but they'll be having shared secret key, which will all be known to them, and those keys must be same. For calculating, they'll be using the shared public key. Power the private key known to them. That is their private key, mod P, where P is the selected prime number. So 9, which is the public key of Bob, mod 5, where 5 is the private key of Alice, mod 13, where 13 is the prime number. So after calculating its value, we'll be getting the shared secret key as 3. Now, similarly, Bob will also try to calculate the secret key, which is 2 power 4, where 2 is the public key of Alice and 4 is the private key of Bob, mod 13. Its value is 3. So we can see that both the values are same. We can say that the algorithm worked fine in calculating the values. So if any more doubts, you can ask me now.
Yes, ma. Jay, you only ask, select any students and ask the questions.
జై ఇంతకు ముందు పీపీటీ ఇంకోసారి.
JD.
ఇంతకు ముందు పీపీటీ ఇంకోసారి ఎక్స్ప్లెయిన్ చేయి.
So, the Diffie-Hellman algorithm in general is used for key generation, that is secret key generation, and only used for this secret key will only be known to the sender and receiver. It will not be shared across the network. And this Diffie-Hellman algorithm is not either used for encryption or for digital signatures. That is, we cannot authenticate that we are receiving this value from Alice or we are receiving this value from Bob, or we cannot even provide confidentiality. But the secret key can be used in other encryption algorithms where to provide further security. So we'll be seeing how this secret key is calculated. First we'll be selecting a prime number in random. And for that prime number, we'll be selecting a generator or an alpha value. For our example, we'll be considering alpha. And this alpha value must be less than the prime number we have selected in random. That is, in this case, it is 6, which is less than 13. And this 6 must be primitive root of 13. What is primitive root? We'll be seeing now. So primitive root is something that is, if we calculate the primitive value, that is 6 mod 13, until 6 square mod 13, 6 power 3 mod 13, 6 power 4 13, until 6 power 12 mod 13. We'll be getting the values like 1, 2, 12. We should be getting the values from 1 to 12. That is q minus 1. That is 13 minus 1, which is 12. And those values must the generated values must not be repetitive. Like if we calculate 2 power mod 1, it is 1. And if we calculate 2 power mod 7, it is 1. And if we calculate 2 cube, which is also 8 mod 7, it is also 1. I'll be writing it. For instance, let us assume we have selected the prime number q as 7. Now we should be now generating a alpha value which is less than 7, and it should also be the primitive root of 7. So we'll be seeing how it is calculated. For it to for value to be a primitive root, let us consider alpha as 2. Now for 2 to be a primitive root of 7, we should follow this procedure like 2 power 1 mod 7. Its value is 1. Next we'll be having 2 square mod 7. Its value is 4. Now for 2 power 3 mod 7, we are getting 1, which we have got in the first iteration as well, where we have calculated 2 power 1 mod 7. So 1 is repeated. So it should not be repeated in the range until this 1. So we should not be selecting 2 as the primitive root of 7. So we'll be checking for 3. So for 3 mod 7 is 1. 3 square mod 7 is 2. And we need to calculate until 3 power q minus 1, where q we have selected is 7. So q minus 1 is 6. 3 power 6 mod 7. Its value is 1. No, okay, its value is 1. Here its value is 3. So in between we have to calculate even for 3 cube mod 7, 3 power 4 mod 7, 3 power 5 mod 7. We'll be getting values like 3, 2, 6, 4, 5 and 1. So we can see that we have got all the values from 1 to 7. That is 1, 2, 3, 4, 5, 6, and none of the values have been repeated. So we can say that 3 can be used as the alpha value, which is the primitive root of 7. Now coming to our example, we have selected prime number as 13, and we have selected a primitive root 6, which is less than 13 by following the above set procedure. So from 1 to 12 values have been generated for the primitive root of 6, and none of them have been repeated. So we can take primitive root 6 as the primitive root. Next, we'll be selecting a private key for randomly. So we will not be checking if it is a primitive root or the prime number. We'll be just taking in random, and those private values, private keys must be less than 13. It is the only condition. Next, after selecting the private keys, we'll be calculating the public keys. Now for in the second step, let's say at the Alice side, we'll be calculating the public key like this: alpha power private key mod q, where alpha is the alpha value is 6, a private key value is 5, alpha value is 6. So 6 power 5 mod 13, which is 7776 mod 13 is 2. So public key of Alice is 2. Now we'll be repeating the same step at Bob's side. So the alpha value, which is 6 mod private key, where private key of Bob is 4 mod 13, where 13 is the prime number we have selected in the beginning stage. and its value is 9. The public key generated is 9, which is shared across the network. Like 9 will be shared to Alice and 2 will be shared to Bob. And the shared public key values will be used in calculating the secret key. So secret key is calculated in this step. So shared public key, that is in for the instance of Alice, will be using 9, which is the public key of Bob, mod power 5, which is the private key of Alice. As I said, shared public key, that is the public key of the Bob, power private key of Alice, which is 5, mod 13, and its value is 3. Now we'll be checking if the value is same as it is in the Bob's case. So in Bob's case, the public key will be using is 2, which is the public key of Alice, and the private key 4 of Bob, mod 13, and it is also 3. So we can say that the procedure we have followed and the primitive key we have selected is correct. And both the private keys are, so shared keys are same. These shared keys will be used in further encryption steps. Encryption steps. So in final, we can say that Diffie-Hellman algorithm provide provide security. That is, key will be shared key will be secure even if in used in insecure channel, and the sender and receiver will not have the prior they'll not have any knowledge of the key being generated. And communication can also be made through insecure